I will. Yeah, I wear it at the last minute, but I guess it's
I'm Xiao. I'm one of the helper of this lecture.
okay.
If you need me to do something, you can tell me.
Okay. So did you receive my email? Or?
Yeah, I received your email.
Okay, cool. Nice to meet you.
Hello. Okay, so we are about to start the last session for the day, and then you can go and enjoy the beautiful, typical London summer. So our last lecturer for today is Sarah Filippi. So she is a lecturer in 2 different departments, in mathematics and in public health at Imperial. Before that, she was at Oxford, and then before that also at Imperial. But she actually did her PhD in reinforcement learning. This is a dark secret from her past that I just found out. So today she will talk about a very interesting topic. So, Bayesian computation is all very well if you can write the model, but maybe sometimes you can't. And then what do you do if you still want to be Bayesian? And so Sarah will tell you the answer to that question. So, thank you.
Thank you very much, Arthur, for the introduction. Can you hear me at the back? Yeah, great. So, I'm very glad to be here and to see all this audience. I'm glad that you managed to be on the 7th day of this very intense summer school. So as Arthur said, I did my PhD in Paris a while ago. Let's not think about dates. On learning. And during my PhD, I did an MLSS, and I learned a lot. And I met a lot of people too, who I still follow. I'm still meeting with them, and some are my collaborators, some are people continue to catch up with at conferences. So I hope you can all have a way to catch up later on, because that's a great way to meet people. So I did a PhD on reinforcement learning, and at the end of my PhD, I thought, okay, now we can use reinforcement learning on many things, but we need to be able to interact with a model, and I want to apply to my research to biology. Now there are some work that can be done with reinforcement learning and biology, and I will work on that in a few years. But at that time, nearly 10 years ago, they were not. So I said, how can I use computational statistics to help the medical field? So I completely left the reinforcement learning field. My PhD supervisor were not that happy. And I decided to work on computational statistics for biomedical problems. And this is really the 2 types of work I do. And when I say 2, I really do kind of half of my week on each. So I developed stochastic model for biomedical problems. Many problems. It can come from clinical data, biologists. Ideally, I want to understand cause of disease, how do they work, and if possible, find treatments or intervene. And the data I write here, they are potentially large, because sometimes it's challenging to have large data sets. Sometimes it's even more challenging to have small data sets, because you don't have a lot of information, and doctors want to find many things from small data sets sometimes. So I have large and small data sets, and I have to solve many different questions. The second part of my work is to develop new statistical methods. So I want my method to be scalable, to be robust. When I say robust, is that in biology the data are really noisy, and you want to take that into account. You cannot just trust the data as if they were coming from a normal distribution or Laplace. No, they are not. They are very noisy. You want the method to be flexible, to be able to adapt to different models, and you want to take into account mainly this idea that the data are noisy. So that's why I wanted to be Bayesian. It's not really I wanted. I came to people and we found out that we could only work with Bayesian modeling if we wanted to take all that into account. So that's my work. I have a second slide to present myself before going into ABC. So that's maybe a summary of my research. So there is the decision process under uncertainty, which is the reinforcement learning part or experimental design. And now I'm trying to do some experimental design for cardiac modeling. So again, decision process. A lot of Bayesian inference, and I'm going to talk about that today. Parametric, non-parametric, ABC, but more recently I did some HMC. Oh my God, you've heard about that today. So I also use Stan a lot, but I'm not going to talk about it now. You had a lot about that. I work a lot now on developing new methods to identify causal effects and identify relationship between variables, a lot in gene and genome-wide association study. And in terms of biology, I tried to put 3 pictures, but in fact there are much more. But I started with system biology, where you have a model and you want to infer parameters. That's what I'm going to talk to you about a lot these few hours. I've done some single-cell genomic, where you can learn a lot about how your body is working, how cancer is working. If we could, that would be great. And how different diseases are working. And now I'm in a public health department, so I work a lot also on global health. So that's to give you like an overview of what I work on. Also because if you want to talk about different things after or during the breaks, etc., I'm here until tomorrow afternoon, and we can talk about many other things that are on the ABC. So to come into ABC, I started doing ABC when I worked on system biology. So just after my PhD, I joined a system biologist group. I was very lucky that they wanted me, but I was just doing reinforcement learning, and I didn't do anything on Bayesian. And they have models in system biology. So here is an example of a model they have. You don't need to know anything about biology. This is a cell, or the gray part is a cell. There is a cell membrane. There are some sins, growth factors that bind to the cell, and that leads to a lot of reaction happening in the cell. They have models of that. They have models of how things react into the cell, etc. But they don't know how to estimate the parameters. They also have different type of model, and they want to know which of these models do explain my data the best. So that's what system biologists do every day. And for that, they need some method. Parameter inference, model selection tools. So here is an example, and that's the data we collected. No, I didn't collect any data. The collaborator collected and gave us, that's a time series. And we had various models. So here I gave one example of a model. The model is not that complex, but still there are 16 parameters, which is feasible, but it starts to be big for a lot of Bayesian methods. There are 2 initial conditions to estimate too, so that's 18 things to estimate. And we observe 9 species, so it starts to be a bit complicated. And we used ABC in that case to infer the parameters, and the fit here is the best fit we found using ABC. So that's how we managed to, that's the posterior predictive. So that's where I started basically 10 years ago, just after my PhD. So what is ABC? So ABC is a statistical framework to do Bayesian inference and model selection in general. The main idea of ABC is that you don't need to have a likelihood. You just need to be able to simulate data from your model. So you need a model. If you don't have a model, we stop here, you can leave the room and don't need to continue to listen. So we need a model, and that's the case for most of the statistical or machine learning approaches. You need a model. If you have a model, you can do ABC. Just so that you know about the literature, ABC is also called likelihood-free inference. So if you look at one or the other, both are done. So ABC stands for Approximate Bayesian Inference, Bayesian Computation, sorry. C, not inference. So computation, you know what it is. Bayesian, you know what it is. I will talk about the approximate part. So as the title says, it's not going to be an exact method. So we are going to make some approximations. I give you some notation so that, and I will try to keep this notation for all the lecture. That's quite tricky. So I assume we observed a data set, and it's calling X star. That's the data set you've observed. It can come from anywhere. Hopefully it comes from the model. It might not come from the model. You have a data set. And then you need a model that depends on some parameters. So I call that a parametric model. The idea is that it's just something that you can plug in the parameters, it gives you an output. So theta will be the parameters, and if you give theta to the model, it gives you an output. Maybe X star, maybe something else. So I will call F this model. So F, given theta, will produce X. X can be stochastic or deterministic. Most of the time it's stochastic, but it could be a deterministic model. We can also call it the likelihood function, but I'm not going to be interested into the likelihood function much because I will assume that we don't know this likelihood. But the likelihood function, you've heard about it on MCMC, I'm sure, even though I missed the beginning of the MCMC lecture. That's likelihood function. So our aims are twofold. The first one is to do parameter inference, so learn the posterior distribution over the parameter theta. And the second one, and we'll discuss about the second one only tomorrow, is model selection. So imagine we have many candidates model, so we have many of these simulators. We want to know which one best explains the data. So in the Bayesian setting, we combine different types of information. So we have the information about the model, which is based on the likelihood, the function f, and we have the information about the prior. So this is the information that we have about the parameter theta. And combining both of them using the Bayes rule, we obtain the posterior. Are you all familiar with the posterior likelihood? Yes. I hope you just follow the MCMC course, but better to check, because if you're lost here, we need to stop and discuss. So you can check that there is a typo in this slide. Can you find a typo in this slide? Yes? So F is the likelihood, so that's fine. It's on the figure on the bottom, and that's why it's a typo, because I didn't manage to, I don't have the original file of the figure. Exactly. This is not equal. This is proportional to. Thank you. So if you multiply the likelihood and the prior, you have something that is proportional to your posterior, but not equal. And that's quite important for a lot of methods, because quite often you cannot compute the denominator. Well, you have probably talked about that on MCMC, but that's often a problem. So that's a probe too. So if you knew the likelihood, if you could compute this function f, then you have many methods to do Bayesian parameter inference. First, if the prior distribution is in closed form, then you can compute, if the prior distribution is conjugate, you can compute the posterior in a conjugate way. There are a few families of conjugate priors, but that's possible, and we will see one in the tutorial tomorrow, just to make things simple. But most of the time, priors are not conjugate, and you need to use computers to compute the posterior distribution. So the most common one are important sampling. Do you know important sampling? Yes? Okay. Markov chain Monte Carlo? If you tell me no, Michael needs to leave just for a minute. Population Monte Carlo? Maybe not. Sequential Monte Carlo? I should have written Hamiltonian Monte Carlo. Especially that I used, I'm sorry, I should have done that. So, but I put 3 dots. There are many others. So that's if you know the likelihood. here I will put myself in a context where we don't know the likelihood. So in many places, we cannot compute this function f. There are many examples. Most of them come from population genetics. So ABC started in population genetics. I'm not a specialist in population genetics, so I decided not to put any example on that because I don't want to say big mistakes. But in population genetics, for example, you can simulate, but you cannot really compute this likelihood. In ecology, that I'm more familiar with, infectious disease, astrophysics, or any biological process or any processes that you can describe by a stochastic differential equation, but that is too complex to compute the likelihood. In all these cases, you have a model, you can simulate for this model, but you cannot compute the function f. In this case, you use the approximate Bayesian computation, or the likelihood-free inference. Here's an example. It was first introduced by Tanaka and Al in 2016, but the figure comes from this very nice review by Lintusari. And we are going to go into this example a bit later on. So that's an example where it's quite useful to use ABC. So for example, for the spread of tuberculosis, you can write a model. You can say, oh, this person can infect this other person with probability alpha, and then this person might contaminate someone else, and the person can die with some probability. So you have a model. You can put that in a computer. That's fine. It might be a very complex model, a lot of lines of code. It's feasible. But there is no likelihood. So if you put as an input to your model the parameter, like all the transmission rate, etc., you have an output, maybe the number of people who died or the number of people who had tuberculosis at a certain moment. But you cannot say what is f of x given theta. There is no measure of the likelihood. So we'll go through this example later. So that's what ABC. ABC is the main tool for parameter inference when we have a complex model for which we cannot calculate the likelihood. The main reason why people use it, in particular in biology, is it's very simple to implement. You will see in the tutorial tomorrow a few lines of code, and you have the basic algorithm. It is very intuitive, and it is super parallelizable. So tomorrow I will use just a basic computer, but you could do it super quickly using a cluster. So that's the outline of the rest of the talk today and tomorrow. I'm not going to cover all that in one session. So today I'm going to talk about the ABC method, the basic, how we deal with some more complicated data and using summary statistics, how we do some post-processing of ABC, and some theoretical results to know what kind of guarantee do we have. Once this is done, you can all go to sleep and rest and be fresh tomorrow morning. And then tomorrow morning we will talk about efficient ABC algorithm and ABC for model selection. So to do ABC, you need all these elements. You need an observed data. You need a prior. Okay, that's for any Bayesian method. You need a simulator, potentially stochastic, so that's my model F. Now there are new things that you need that you didn't need when you do MCMC. You need a distance to compare the simulated data and the observed data. I will explain you after how we do that. Then you need a threshold to determine how far away you want these two things to be. And of course, you need computational resources. Because I told you that it's super parallelizable, and it is. However, if you want it to be efficient, it can take a long time. Now we have great tools. But when I did my ABC a few years back in the system biology, some of my programs were running for weeks. I can tell you that you don't want to have any mistake in your code. Huh? If after 3 weeks you realize that, whew, my data were wrong, you have to redo it again. Hopefully you have a second project to work on at the same time. So that's the idea of the algorithm. The idea is there, and that was introduced first by Tarare in 1997, quite a while ago. So imagine you have this observation. The idea is very simple. You sampled theta from the prior. Then you simulate your model using that parameter theta. You obtain a z, which is the output of your model. If z is equal to x star, your observation, you accept theta. If z is different to x star, you reject theta. and you keep doing that. So you sample theta from the prior, you simulate your model, you obtain an auxiliary variable z. If z equal to x star, you say, great, I accept it. If it's not equal to x star, you reject it. Since your model is probably stochastic, it might give you different value of z, and you might have many parameter value theta that will give you z equal x star. So at the end, you obtain a sample from a posterior distribution. Okay? So that's for some notation that I will use all over. Theta 1 to theta n, when I use this thing in parentheses on subscript, are all the samples coming from my distribution. So itself, it can be a large parameter, but it's all the sample. And so these resulting parameters follows the posterior distribution. Why it's very easy to... There is another typo here. That's now that I see the typos. That's always like that. So don't look at that. This is the output of my algorithm, the first part. What is it? I sample theta from the prior. I simulate from the model. And then I only accept the one such that z equal x star. I do that many times, so that's why I integrate over dz. If you plug it in, you have x equals z star, so you replace here z by x star, and you don't have dz anymore, and you obtain exactly that, which is the posterior distribution. So basically, this algorithm gives you exactly the posterior distribution. Yes?
What's the difference between a simulator and a likelihood function?
So that's the same, except that we don't evaluate the function. So when people think about the likelihood, they think about this function. For one value of theta, we associate f of x star given theta. Here I cannot compute that. I can simulate from the model, but if you give me a value of theta, I cannot tell you what is the probability of x star given theta. You see what I mean? That's a very good question because it's essential in ABC. So we can simulate the model. Imagine this tuberculosis example. So the parameters are probability of transition of the disease from one person to another. So if you give me some parameter value, I can put it in my model, and it gives me at the end how many people are unwell at different time. But if I give you the output, you cannot tell me what the probability of this data given theta. Yeah?
What was the type?
Sorry?
You said it is a type in the grade.
I never have defined f, so I don't exactly know what f is here. So that's not that important. I just realized f is nothing here. It doesn't mean. Yes?
Do you mean for a fixed theta, you simulate several times as long as it can give you a z which equals to x star?
Yeah. Yeah.
So how do you determine how many times you simulate?
Sorry?
How do you determine how many times you simulate z or fixed theta?
So you simulate as long as you have z equal x star. And you do that many, many times until you have n sample. Does that answer your question? Or not? I'm not sure I understood the question correctly.
So I mean, for a fixed theta, how many times you simulate z?
So you repeat that many, many times until you have the real. So you repeat these procedures as long as z equal x star. That can take years, huh? That's why this is not the ABC algorithm. Huh? So I will go to the ABC algorithm and take a few more questions after, if you don't mind, because that might answer your question. So in practice, this is impossible, because except for some value of x star, it will take forever to have a z exactly equal to x star. So the idea is to replace that by a tolerance, and you will just accept when the distance between x star and z is small enough. So that's more the idea of ABC. And that's why it's approximate, is that because we will have this epsilon that we'll play with. If epsilon is equal to 0, that's the first algorithm, but in most of the real life, or even not real life case, if h is continuous, that will not work. So what we'll obtain at the end is a posterior distribution, posterior of theta, given that the distance is smaller than epsilon. And so this is the algorithm. I'll answer that just after. This is the algorithm written in an algorithmic way. So you have an observation as an input. You have the number of particles n that you want to have at the end. Imagine you want to have a sample of size 1,000 at the end. You have a threshold, and you repeat. So for I from 1 to n, you repeat this procedure. You sample theta from the prior. You simulate your model. You compute the distance. If the distance is smaller than epsilon, you accept it. If it's larger, you reject it. And you continue to do that until you accept one. Once you have accepted it one, you call it theta I, and you repeat from I from 1 to n. Again, that can take a very long time, especially if epsilon is small. If epsilon is large, you will nearly always accept, and that's fine. But you will do a big error, because the distance will not, it will be very far away from your real data. So I can take a few questions now. Yes?
2 slides before.
Yeah?
Yes. Auxiliary variable z from the simulator.
Yeah.
F is the stochastic function that will output z.
Yes.
Okay. So if z is rejected,
Yeah.
what do we change? Do we sample a new z, or do we change theta before sampling z?
That's what we do. So if z is rejected, we repeat. We generate theta from the prior. So we don't, you see the repeat is, I don't have a point, I have a pointer here. So if we generate z, we compute this distance. If it's rejected here, we repeat it there. So we generate a new theta. And then we generate z. And then we check. And we repeat again here. So we don't regenerate z from the simulator. We go back to theta.
Okay. And then in the previous slide,
This one?
yes, the Poisson distribution, but pi of theta d equals
Yeah.
x star z.
Yeah.
This t is computed, but we still have the stochastic
Yeah.
simulator.
We always have a secret stochastic simulator F. From now on until tomorrow too, you have a stochastic simulator. With you, even tonight. You dream about it. Okay, yes?
So I'm quite intrigued because the simulator you can't write down, so you can't really analyze what it does. So how do you know that you can actually get into the epsilon neighborhood of your x star in the first place?
You don't know.
Okay. This could run forever.
So basically, there will be a slide about the choice of epsilon. In practice, if you are just here, but then I will explain you a bit more, you try some epsilon, and if it runs forever, you say, oh, I'm not ready for that. You try a larger one. Okay? But I will give you some tips of how to do. I take 2 more. Yes?
So I know epsilon will definitely contribute to how long it takes, but do we have to be smart about how we choose the priors then? Because it seems like it's very dependent on sampling stuff from the prior. Do we have to think a lot more about that in this case?
So yes and no. Yes, because if you have a prior that is very informative, it will help. But usually, all your inference depend on your prior. So imagine you had an exact way, even if you just do an MCMC, it depends on your prior. So your prior should be set in advance, whatever how the problem is. So it's usually bad practice to just say, oh, it's too difficult to do, I will change my prior. Prior usually summarizes the information you have a priori. So you should not. Then if you think, oh, first I did a prior that was very simple, and then I'm like, oh, by the way, I knew more things. Maybe I should take that into account. Yeah, if you have a prior that have more information in it, please do use it. Yes?
So sorry, I'm going to go a bit back, I think, but no, not on this slide.
Okay.
So you mentioned this example with tuberculosis as an example of a likelihood-free problem. But can you give us like a concrete, small example where we can't evaluate the likelihood?
Smaller than this one.
Yeah, just like a particular model where we can't evaluate the likelihood.
Trying to find a very simple one. I will give a couple after, but they are not super simple. But yeah, one of them that I'm going to give later is just a stochastic process with 2 steps. we have it in a few slides, so I'm not going to give too much details. And basically, it generates a time series. If the time series is small, it's computationally tractable. If the time series is big, here's not that you cannot compute likelihood, is that computationally it's super tricky because you have to integrate out a lot of intermediate variables. I think the tuberculosis example is maybe the simplest in a way, because it's really a model where you cannot compute the likelihood. You could simulate it, but you cannot. You know, you just have to think about a black box where you don't have a model of the error. So if you have a black box that just simulates from your data, to have likelihood, you have to model how the error is in your black box. And that's what I do when I do MCMC and when I use STAN. I construct a likelihood, but I know my likelihood is wrong. If you don't want to do that, and you just have a model that doesn't give you a probabilistic approach, I hope the example after will be a better way to explain. So that's just an illustration. I don't have a movie, but that's nearly a movie. So imagine you have a model in 2 dimensions. Now there are 2 parameters, θ1 and θ2, and you have some data that are observed here with some confidence interval. That's typically what I have when I have a very nice data set from biologists. Sometimes it's not that nice, but if I have. So the idea from ABC, I sample a point from the prior. My prior is just this blue rectangular. I simulate data from my model, and I decide, I compute the distance between the data. So my simulated data and the observation, and I'm like, that's quite far away. Let's reject it. Compute the distance. It could be a Euclidean distance. It could be anything. So I've rejected it. It's in gray. Now let's take another sample parameter from the prior. We simulate. That's pretty good. The distance is not that bad. Great. Even for a quite small epsilon. I like this one. Let's accept it. And I do that many times. And I will have some that are accepted, some that are rejected. And what I obtain at the end is this thing, these particles. Here I have 7 of them, if I count well. Hopefully we'll have much more, because 7 is not really enough to do any posterior. But you have, and that's a sample from your posterior distribution. So that's really an illustration of how it works in practice with some eyes. Yes? We never decide to change prior.
So what if the prior is wrong?
If the prior is completely wrong, I will more say that your model is wrong, because the prior is with the model then, and we are under model misspecification. I will have one slide on that today, but it's not the scope of this tutorial, and we can talk about it later. There is a lot of work on model misspecification. What if your prior is completely wrong? Then there are work on that. Yes? You're more going to be underfitting, because it depends on your epsilon. Here I had a very, very simple example, and that was trivial. But many of them would fit. So no, a priori, there is no worry of overfitting the data on that.
I guess it depends on the epsilon also.
Of course, but even, we want epsilon to be as small as possible. Because if epsilon is 0, that's your exact posterior. Another question?
It depends on the model complexity, even if you don't know your model. So, for example, let's say a black box, and you consider a neural network.
What do you mean it doesn't depend? What doesn't depend?
The answer. I mean, the
answer to
you're getting.
Okay.
Does it depend on the model, on the data complexity?
So basically, of course, if the model is complex, for a given epsilon threshold, it will take you forever to obtain a sample. So yes, there is, of course, a trade-off between model complexity and epsilon, etc. But theoretically, if you could run it forever, which we never do.
The question basically how complex the task you can solve with this approach. So it seems to me
in practice,
relatively simple.
So in practice, because you have now clusters and with a lot of computer, which I didn't have when I ran that, it's not that complicated because it's completely parallelizable, huh, what I've done. You can run it, a lot of particles in many clusters, and that can deal with very complex models. That's not the most efficient way to do. Tomorrow I'm talking about the most efficient way to do. But in theory, especially nowadays that you can have access, if you can have access to a computer cloud and using many, computational resources, that's fine. Yes?
Why do you call it particles?
Sorry?
Why is it called particles?
Oh, why is it called particles? Does someone know? Sorry? I don't know. I don't remember. It might come. Like, Michael, do you know why it's called particles?
I'm going to guess it's the particle filter reference.
Yeah, do you think so? All my PhD supervisors were from signal processing, so it might be that, but I might be wrong.
Sorry, just a clarification on the previous slide. Do we assume that the data are deterministic, and these error bars are basically just the epsilon distance, or is this measurement noise from the data we collected?
So I will come to that later. So ideally, the algorithm I just presented was more if we consider only the mean, for example. If we don't consider only the mean, we'll need to take into account some summary statistics. I'm going to that soon. Yes?
The second thing, we only make a prediction at a finite number of locations at the data point, right? We don't have this smooth function that we use.
My model here did that. You could have many models doing many things. And it doesn't need to be a time series. It could be many things. Here, this example was that I was making prediction at this time point. You could have many, many other things. I take one more and then I have to continue. Yes?
Just a clarification. So the model is the prior,
Yeah.
and then what's the simulated? How do you...
For this example?
Yeah.
Oh, that's a made-up example. So here I assume that we have a stochastic differential equation, but it could be anything. Like, that's not even an example, and that's just an illustration of how the algorithm works. I will go to an example in a few minutes with a real example, real application. So where am I? The output of the algorithm. So what we have at the end of the day is this theta and this z. This z is the simulated data. And so we have the posterior of this theta z with a given epsilon. So here is what I called pi of theta z epsilon. So epsilon shows the dependence of the threshold. And that's the joint distribution. So we sample from pi, we run the simulator to obtain z, and then we accept, reject, depending on is the simulated data far away or closer to the observed data x star. And then we normalize to make sure that it's a density. It's a probability. I write it down because it might be important later on for some theoretical results. And what we care about is not the z, so we compute the marginal over z. So we marginalize dz, and that's what we obtain. So the basic idea of ABC is that when epsilon goes to 0, this thing goes toward the real posterior pi theta h star. If epsilon is large, we are going to be far away from the real posterior. If epsilon is small, we'll be close to the real posterior.
So the way you're describing it looks like metropolis testing in a way.
What do you mean? Why there is metropolis testing?
Yeah, you like sample, then evaluate, then reject or accept.
That's Bayesian, no?
What if you keep rejecting?
Ah, yeah, I see this way of metropolis testing.
Yeah.
But if you keep rejecting, you will not have a posterior. If epsilon is too small and your model is too complex, you will keep rejecting.
So it all depends on how much tolerance you accept? Okay.
And on your distance. And on something else that I'm going to present soon. So epsilon should be officially or theoretically as close to 0 as possible. Because when epsilon tends to 0, we obtain the real posterior distribution. But the choice of epsilon, as we just talked about, is quite important. So small epsilon are associated with a high computational cost. That's quite obvious. We are going to reject much more often. In practice, there is this method by Beaumont and al., which is to select epsilon as a small percentile of the data. So the algorithm is slightly different, the one they suggest, is now you don't do the accept reject, you always accept. So you decide, okay, I'm happy for a budget of 10 million, it's a lot, huh? I'm happy for a budget of 10 million, so I'm going to simulate sample from the prior 10 millionth time, simulate my model 10 millionth time, I will have a theta and a z, 10 million of them, and then I will say, I look at the distance between this z and the real observation h star, I look at this 10 million distance, and I will take a quantile of that. So I will say, okay, I will only take 1% of these 10 million. That's a choice of epsilon, and that's a way where you can really control the computational cost. There are other approaches that I'm not going to talk about that are more where you infer epsilon at the same time. I'm just going to say next slide because it repeats what I've just said, so it might clarify, it might answer some of your questions. So the idea is now you have n fixed, and you will simulate n time. You're not going to do this accept reject. For n time, you will generate theta from the prior. You will then generate z from the simulator. You will do that n times, so there is no accept reject. Then you will compute some quantile, so we need to define alpha. So you need to say in advance how many you're ready to reject, which percentage. You compute the distance. Oh, sorry, I should not have a eta here. I'm very sorry about that. Forget about the eta. You compute these distances, and then you return only the ones that are smaller than the distance. Just I finished my sentence. The idea is that you know in advance how many particles you will have. Because you simulated n times, you have alpha, the acceptance, the quantile, so you'll know that at the end of the day you will have alpha times n particles. So you fix your computational cost here. You know in advance what the cost of your algorithm will be. Whereas in the accept reject, you don't know, you might do it forever. So yes?
So in this case, you're kind of letting the algorithm choose the epsilon.
Exactly.
Right. Could this also be used to do some sort of diagnostics on the actual simulator itself? Because if it takes you 10 million samples for you to get, for example, I don't know, a very bad epsilon tolerance, is that saying anything about the simulator?
That's again related to model misspecification, that it's a bit tricky. There are some model checking using ABC. Yes, I'm not covering that, but we can talk about it. Yes?
So in this case, won't epsilon be like different for different observations?
Yes, it will. It will not affect the posterior, because the posterior depends on the data. So it will not depend on everything depends on the data anyway. That will not affect that will not affect more the posterior than anything. But it's true that epsilon will depend on the data. Yes?
It's a question of understanding. So in practice, we never have access to the whole data set. We have access to only part of the data, the one that we have observed.
Yeah.
But how sure are we that if our function, if our model that we have match that one, it will match with the other one that we have not yet observed?
So far, I haven't said at all that you are not observing the whole data set. You might observe the whole data set. You have a data. It might be everything. You just have a data set. I didn't say that you're hiding some data away. Huh? X star is all the data set you have. And you do a posterior, you want to do Bayesian inference based on this data. Yes?
When you run algorithms with specific epsilon, you get samples of your posterior, right? So how do you choose the family that your posterior is going to belong to?
How do you choose a family?
Family of distributions.
You don't.
So how do you use it?
You just, at the end, oh, okay, that's a good question. So at the end, you don't have an analytic form of your posterior. You just have samples from the posterior. So this algorithm, like MCMC scheme, gives you only a posterior from the distribution. It will not give you the closed form of the distribution. We could. There are work doing that, but that's the case for any Bayesian inference. Most of the methods produce a sample from the posterior. Then there are some ways if you want to have a closed form, but usually you don't want a closed form. Okay, let's start with an example now. We wanted some example. We have one. So this is a stochastic process. So that's a stochastic process that generates a time series. And the way it generates a time series is that it samples some IID standard normal, which is the U here, and it sums the mu backward with the theta I. So it just generates a time series in a very simple way. For that, we could compute the likelihoods theoretically. On the bottom, there are some typical conditions on identifiability. I don't want to go into the details of that. Just need to know that theta needs to be in certain region so that the problem is identifiable. So let's assume we know that. And a simple prior will be uniform over this set of identifiability region. So why do we use ABC in such a context? So the likelihood, in a way, could be computed, but it's very complex, especially because we need to integrate out all this U, sorry, for my pronunciation. So there are this U involved in the equation, and to have the exact likelihood, we will need to integrate out all possible value of this U, which is itself coming from a normal distribution. So that might be complicated, especially if we have a large number of n. So if we want to sample, if we want to have a long time series, we'll have a lot of these nu to integrate, and that becomes practically computationally not feasible to do it. So it's not that it's like theoretically we could, but in practice we cannot. Again, MCMC is feasible, but computationally very tricky in this case. So except if we do toy example of that. So here, running one iteration of this ABC problem, it requires to simulate the coefficients. There are two coefficients here. Well, no, sorry, where there are two coefficients, theta, all the theta, from the prior, then generate the U, and then compute this model, this sum of the U using the equation from the previous slide. That's pretty easy to do. That's just a simulator. Huh? We'll compute it tomorrow. That's 2 lines of code in Python. So the simulator, very easy. We can consider different distances, and here I suggest to use 2, suggested by Mara and Al. One is just the Euclidean distance between the two sequences, and another one is based on the autocovariances that a lot of people use for time series. So what do we obtain? The triangle here is all the region of possible parameters. As I said, there is a region for identifiability. So imagine that we know this region in advance. We know that this is the region of possible parameters. The real parameter is in red. I don't know if you see the red dot. So the value of theta is 0.6, 0.2. So that's the real parameters. We consider the model with just 2, so Q equal 2 here. And we used ABC. We used it with n equal 10 to the power 6 simulated data. That's a lot. And a threshold epsilon of 0.1 of the quantile. And what we obtain is this blue thing. So here in black is the real posterior distribution that, as I said, we can compute in some cases, especially here, Q equal 2 is feasible. It's tricky, but it's feasible. So imagine I wanted you to be able to compare. So on black is the real posterior, on blue are the posterior obtained by the ABC. It matches, but not perfectly. Well, that's an approximate distribution. No? Yes?
In black is a true posterior?
Yeah, on black is a true posterior. In blue are samples from the ABC algorithm.
And red is the true?
Red is the true. The parameter that has been used to simulate the data. You know, as always. So I have a black box. I have a model. Theta is used to generate the data, but it's not the maximum likelihood. The maximum likelihood will be at the top of this, depending on, it's a uniform prior. So the maximum likelihood will be in the middle of this black area. Okay? Here is the marginal for theta 1 and theta 2. So now I just look at the marginal. The black, again, is the real marginal density. And then the different colors, so blue, red, and yellow, are when we decrease epsilon. We see that when we decrease epsilon, we are getting closer and closer to the truth. not completely directly. Here on theta 2, we see that we are still not there. But we are getting closer and closer. If epsilon goes to 0, yes?
Why is theta 2 so complicated?
Why theta is not?
Theta 2, why is that one so complicated? Theta 1 seems to be relatively easy.
I don't know. My guess is that it's a time series that goes 2 times back. So that might be a reason. But I'm not specialized in time series. If it were a biological model, I could more give you an intuition. Oh, yeah?
Out of curiosity, what does MA stand for? Okay.
Thank you. No worries. Yes?
When you vary epsilon, do you then increase the data so that the amount of data points that you accept stays the same as you vary epsilon?
So here, n, the computational cost remain the same. Does that mean that I'm too slow? Is it like a way to say, hey, guess account username? What should I do? It's on my computer?
Yeah, it may have switched to the...
Okay, can you... but mine didn't go off.
Maybe do questions while this thing...
Yeah, great. So, sorry, what was the question? Yeah.
So you're actually...
Oh, yeah, I remember the question now.
You're looking at two effects, right? So the approximation gets worse, but at the same time you also do all...
So, sorry, now I remember the question. The answer is that here n is fixed. So, n, the number of simulation is fixed.
Right.
So, we are using the one based on quantile. So, n is 10 to the power 6, I think. N is fixed. We have 10 to the power 6 simulation. We've done it once. We just change epsilon. Is it getting solved or, yeah? It's going to.
It's running Windows.
Great. So I take more questions. Yes?
So if you set the threshold really low, and you end up with like a few points, is there some intuition about is that better than getting setting epsilon a little higher and getting more points? Because like if you set it, is it always like you set it lower and maybe you get something across the threshold that's good, or is it?
So that's a very good point. I have an illustration on that. I don't know when, a bit later, where we could put epsilon to 0, but in fact, if you use this, it will take forever. So either we accept to only have a few sample, but then it might be a Monte Carlo error because trying to find we only have a few samples to summarize the distribution, or we can just take much longer and be ready to do that for months. So that's, I have a nice slide that do that on the tuple electrolysis example, the trade-off. Yes?
What is the conditional D for convergence? Because I could, for example, just say D of xz is always equal to 0.
So this is a distance, and so far any distance could work. As I had in the next slide, I had an example where showing that using two different distances give you different results.
If I just said Exz is always equal to 0, regardless of what I put it.
D needs to be a distance. Huh?
Oh yeah.
D needs to fulfill the distance. So D of, all the distance, I'm not going to cite all of them, but it needs to be distance. It cannot be constant to 0. Yes?
Is there any results about natural distance metrics for certain problems? So you had moving average processes there. Is there a natural or best distance for that? I understand that in practice maybe you don't know what the model is, but I'm interested in hearing.
I'll touch that in a few minutes. But that's kind of answer half of your question, is here are the same plot as before, but we use two different distances. This one is the row distance, this one is the, this one is the autocovariance, this one is the row distance. And we can see that it gives very different results. And the color is just different quantile. So yellow is a small epsilon, whereas blue is a large epsilon. Yes, I didn't answer fully? Yes, I will come back to that in a few slides. Yes?
There's a question from the internet.
Oh, no.
So the question is, for good Bayesian estimators, the influence of the prior vanishes as we get more data. Does something similar happen with ABC? So
the prior effect vanishes when we have more data. Yes, yes. if epsilon goes to 0,
So if I choose a different prior, would I get pretty much the same result if I have more and more, if my data set is bigger?
if epsilon goes to 0, all the result that holds for Bayesian holds for ABC. Now the trick is that if epsilon is not equal to 0, then we have different results. I have some theoretical results coming later about consistency and the speed of convergence. Yes?
So one thing I didn't quite catch, so D needs to be is defined on the whole data set?
Sorry, D is?
Distance D is defined on the whole data set.
Yeah, D is to compare the simulated data set to your real data set. There are many ways of defining D. You can define it in subset if you want, but every distance is valid, as long as it's a distance. Okay, yeah?
So for any epsilon larger than 0, the choice of how you evaluate discrepancy from the data to the primal set will change. So I'm quite intrigued by this. I'm wondering whether for different distances you actually encode particular aspects of the model that you want to learn about. So in some sense, you actually perform local perturbations of the model in question.
Yeah, you do. So the distance D is crucial. That's why I wanted to show this example. And I will show in the next slide that it's not only the distance D that is crucial, and then there is some work about how to choose these things. So thank you. You're bringing me to the next point, which is when you're in high-dimensional data, but not only in high-dimensional, but quite often, you cannot really compare X star and Z, or it will really depend a lot on your distance D. So the idea is to reduce the dimension using summary statistics. And that's related to D. So the algorithm is very simple. The algorithm is the same, except that you have a summary statistic that I will call eta for Z and for H star. That's the same summary statistic. Huh? So you have a statistic that summarizes everything. And there are a lot of works on how to choose eta. So most of the time the work is not on how to choose D, but is on how to choose eta, which is kind of similar, because if you know how to summarize your data through eta, then you know how to, well, then it gives you direct control. So that's the most general ABC algorithm. When people talk about ABC, they talk about this one. The most general one is that it's, instead of comparing the simulated data to the real data, it compares the summary statistics of them. So let's go to the example of tuberculosis. Let's drink a bit of water first. So we have this model. As I said, this model is not mine. It's from some Tanaka and al. And I will try to explain it the best I can, but I might do mistakes. Here are the reference to have a precise description if you want to do epidemiology. So the idea is that we want to understand how tuberculosis spread across the population. So imagine that we start with one person, and many things can happen. So the first thing that can happen, or one of the things that can happen, is a transmission. So a color shows that one human has the disease, and there are different colors for different pathogens of the disease, because there are different types of tuberculosis. So here there is a type red, the type blue, the type green, the type yellow, maybe. Okay? So imagine that we know that there are different types. And so one of the things that can happen is that someone transmits the disease to another person. So we had one person infected with the red pathogen that goes to 2 persons infected with the red pathogen, and 3 persons infected with the red pathogen. Then the pathogen inside the body of the person can mutate to become another pathogen. That's one of the problems of disease, is that you can have a treatment for one disease, but in fact, the disease changes in the body of the person. So there is a mutation happening here, and we had 3 persons, and we still have 3 persons, but 2 have this pathogen red, and 1 have the pathogen blue now. Okay? And here, for example, what happens is that the blue spread to another person, so we have 4 people infected, then another mutation, and so we have still 4 persons infected, but with 3 different pathogens, blue, red, and green. Oh, and what happens here? Someone died or get healthy, and so we only have 3 persons. So in the model, dying or getting healthy is the same, which is not very nice. Huh? But it means that, because we only care about how many people are sick with the disease. That's great, huh? So we are back here. What happens is that some of the pathogen are mutated, so we are again here. Here what happens is that we stay here for a while. Then we can again spread the disease, and so you understood the principle. So we can do a simulator of that. That's pretty easy. Huh? I haven't coded it up, but imagine you could code it up. And the output of, so the input of the simulator is some parameter that I will describe after. The output of the simulator is how many people do we have in each cluster. What they call cluster is red people, blue people, red, green, with different pathogen. So here the output will be 2, 1, 1, 1, because there are 2 red, 1 yellow, 1 green. We don't care about the order. So we just say that there are 4 different colors. So it's a list of 4 with 1 with 2 and the other one with 1. And that's the output of the simulator. That's a simple simulator to code up. That's not such a simple simulator to have a likelihood. Because what would be a likelihood? I don't even know how I will make a likelihood out of that. There is no error model. There is no... So that's a stochastic thing, huh? Because it happens stochastically. But there is not real likelihood. So that's kind of the example I had in mind. That we could say, oh, this is with some error, but yeah. In special case, if we have in very special case, and they say it in the paper, we can compute exactly a likelihood, but it's very rare, basically. So here are the parameters of the model. The transmission rate, alpha, which is how, by the transmission rate, it explains how much we can infect someone else. The probability that a host stops being infectious, delta. So it means someone died or someone gets better. That's a nice way to say it. The mutation rate, so what's the probability that the host pathogen in one of us, hopefully none of us, becomes another pathogen. And what we observe is, so the number of people infected with different pathogens in a subsample of the population. So imagine we run that until we have a huge population of size M. We subsample the population, and then we compute how many people have each pathogen. So here is an example of, imagine we have 20, I don't know if it sums to 20, I don't know what it sums to, and I have 21 here. We have 21 people, 6 with one pathogen, 4 with another, 2 with another, 2 with another, and 1 with each of the other ones. So this is intractable if the population size M is large and the death rate is strictly positive. If M is small, then there is likelihood that is available. It's available, well, if you want to see the derivation, it's on the paper. I'm not going to write down the derivation. So I found that the plot in this paper was really explaining quite well what happens. So here they assume that they have this observation that is on the top here, and they only want to infer the transmission rate to simplify what we have. So we have n equal 20, and they are in a very specific case, and that's why I refer you to the paper, where because n is equal to 20 and is not that large, we could compute a likelihood. So they have a way to compute it, and the real posterior is the black one. So the real posterior is the black one, and here we have different value. So unfortunately, they don't use the same notation as me. So T are the summary statistics. They have 2 summary statistics. One is the number of cluster divided by the sample size. And the other one is the genetic diversity, which is 1 minus sum over I. I is the number of cluster. So I goes to 1 to the number of cluster. And I over n. So for I equal 1 is 6. For I equal 2 is 3. For I equal 3 is 2. So, you know, we have to, so this is this divided by n, and we sum this divided by n plus this divided by n. So ni are this number here. So that's 2 summary statistics, and this shows how, for different value of epsilon, for different summary statistics, we can obtain very different posterior distribution. I let you look at it. So in the first one, we have summary statistics that kind of concentrate. So we can, if epsilon is very small, here it goes even to 0. We can talk about it after why it can go to 0. then we exactly recover nearly the posterior. And when epsilon is off, we are far away. Here we have a second summary statistics. And yes, when epsilon decreases, it converges nearly, but not exactly to the reference. So the choice of the summary statistics has an impact. Yes?
I'm a little bit confused about exactly what, what are they trying to do? I mean, I understand that they are trying to simulate the transmission rate of tuberculosis.
Yeah.
But how do you simulate from reality? What I'm saying is okay, so I assume that they want to model the real transmission rate of TBC.
So I cannot tell you for them because that's the model. I can tell you from my experience using a biological model. So for example, I have some colleagues of mine working on malaria. And we are trying to do a very complex model, so much more complex than that, which takes into account localization also. So it's spatial temporal model. But it's kind of similar if someone infects someone else, etc. And we have this model with many parameters to understand how malaria spreads. And the idea is to do an intervention on vaccination in different villages. So that's the idea, basically. First, we need to infer the parameters in order to, once we have a model that fits our data, we can intervene.
Okay, but how do you simulate? That's what I'm not
Oh, simulate, you construct a model.
So
you construct a model. You think about, you talk with experts of the field, and you're like, how does the disease transmit? Yeah. You assume that there is a mechanistic model that you know. Okay. For all along this talk, I will always assume that you have a simulator. So you have a stochastic model, you simulate from it. Then is the simulator reflecting the reality? That's a question, and that's model misspecification, and then there is model checking. And when you work on real data, that's a problem that you ask yourself all the time. Does that reflect the reality? I just, yeah?
So, sorry, see if I get this right. In this case, we use on the left, we use one summary statistic.
Yeah.
And then we did the whole ABC again for the other summary statistic.
Exactly.
And we couldn't use both, or
we could. Here is just to compare that using different summary statistics gives you different results. An interesting thing here is that they could put epsilon equal to 0. Why could they do that? Because the observations they have are integers. They are not continuous data. If you see, the observations they have are numbers 63221. So you can take for ages, but you can technically obtain exactly the same. So that's why they can technically put epsilon to 0. I don't remember the comment on it on the paper, and that takes for a while. No? But if you use summary statistics, you're not going to converge to the posterior because you're not going to converge to the posterior given the observation. You're going to observe. So the black one, well, how does that? The black one gives you the posterior of theta given your observation. All the other one give you pi of epsilon theta given your summary statistic of the observation. If epsilon goes to 0, that's converged to pi of theta given. But that's not the same. Because one there is an eta, the other one there is not an eta. That's just what we see here. Okay? Yes?
I think I don't quite get the second summary statistics.
Yeah.
Because it will sum up in i's, which are like 6 through y.
So I is all these things here, yeah?
Yeah, if we sum up, they sum up to 20, right? And then the summary statistics, second summary statistics.
Okay, so there might be a typo here.
So I've just looked up the original paper, there should be square around the fraction. So something like n over n squared.
Okay.
Okay.
Sorry.
Okay.
Yeah.
Because it's always 0, and I was just wondering, like, how do you model?
It's completely possible that there are many typos. You know, it's so easy to do typos when you write equations on 99 slides. So, yeah, sorry. I will try to remember and correct the typo and push it to Git tonight with the corrected thing, if I remember. Okay? Yes?
I'm still confused
So the model is the one that I described before. It's a model that describes how people transmit the disease to one person to another, and then how a pathogen inside a person can mutate to another pathogen, and that's it.
So do we know the model? Can we write it up?
Yeah. So here I wrote a drawing for it. We could write it up. Maybe if you insist, I will ask you to do it tomorrow. That's a good exercise, and I didn't think about it, but we could try to write it together tomorrow. It's not that complicated. It's yes?
I have just a little follow-up to the previous question. So the black reference line here is your stochastic model that you built with expert knowledge.
Yeah, the black line is that.
So you're trying to fit using ABC to that model.
The black line is the posterior distribution that we don't know in general, but each time here I try to make examples that are simple enough so that we can compute it in some complicated way. So the black line is a true thing that we are trying to converge towards. But usually, that's always tricky when you present ABC, because either you do real example where you don't have the reference because it's just impossible to compute completely, but then you don't know if it goes to the right. If you want to teach about it, it's better to have a black line to understand if it converges or not. But in reality, most of the case, you don't have the black line. Otherwise, you would not do ABC. You would do the method to compute the black line. You see what I mean? So here, I just do examples that are simple enough to do the black line. At the end of tomorrow, I will do an example, but I will not even be able to write the model, where you have images and a fish and a cell that follows in a fish, and you have no idea what the real model, no idea what the black line is. That's real ABC. Yes?
Can you just use any sufficient statistical interested?
Exactly. So if eta is sufficient statistic, we will, when this will be equal to that. Yes? This is to answer the computational cost question that was before. Is it worth putting epsilon to 0, even though it will cost much more? So on the left is the same thing that you've seen before, nearly, or not nearly, not exactly. So here, as I said, you could do the exact rejection algorithm. So the one that we talked about on the first slide, which is simulate from the prior, then simulate from the model, and accept reject only if z is equal to x star. That can take forever, but we can do it because the data we have are integers. So it's possible. That's the blue line. Is it the blue? Yeah, that's the blue line. That's what they call algorithm 1. Then algorithm 2 with two different statistics. So the posterior are on the left. On the right is much more interesting. Is a trade-off between the KL divergence, so how well you are going to estimate the truth, and the computational cost. So if the KL divergence is small, it means that you estimate it very well. And we see that even though the blue can give you exact results, it will require a very, very, very high computational cost. So at a fixed computational cost, the KL divergence is smaller for the green one. So that's a trade-off. So even when you would be able to do the exact rejection algorithm, you might not want to do that because you don't have exponential time to do your inference. That's pretty rare to have example where we can do that, because in most of the examples, data are continuous anyway, so we can just not do epsilon goes to 0. That's just impossible. Here we can. We just show that even if we could, we don't want to do that because it will take forever. So I already said from the beginning, it was a big warning, ABC has approximate in it. And approximate means that there are errors. We've seen it from already like the last hour and 15 minutes. So there are two types of error. First, there is the error because we use a threshold, epsilon, and if epsilon is not equal to 0, we have this error. Second error is because we use a summary statistic instead of the real data. So we have two types of error. We can control them in a way. We could control the first one by putting epsilon as close to 0 as possible. And the second one, we could control it if we have a sufficient statistic. So if eta is called sufficient, we can exactly control the second error. So if for your given problem you can find a sufficient statistics, and sufficient statistics by definition means that the posterior using the statistic and using the observation data is the same, then you use it, please. But in many cases, either you don't have it or you don't know if it's sufficient or not. So how do you choose the summary statistics? So we want the summary statistics to be a data reduction, a dimensionality reduction, sorry, in the data space. So the summary statistics takes a number from the observation space that I call X, can be any dimension, and gives you a value that is on dimension K. So if K is small, the good thing is that epsilon don't need to be very big. If K is small, you can control the error regarding the threshold, because you will compute the distance between two things that are quite small dimensional. So you can control the error regarding the threshold. But if K is small, you have a problem because your summary statistic will probably not summarize well enough the observation, except if it's sufficient. To the opposite, if K is large, you might have a perfect summary of your data, especially if eta is equal identity, you have a perfect summary of your data. But you might need to play with the threshold in a difficult way, because basically you will have to compute the distance between two things that are high dimensional, and that's going to be very tricky to find samples so that the distance is small. So that's a trade-off. So ideally we would like K is equal small and eta being as informative as possible as a sufficient statistics. I just go to the, oh yeah, no, go ahead. And,
so is another thing that kind of comes up that, you know, since we're choosing a distance between summary statistics, even though these are the two kind of considerations, do you also think about like what distances are, like what summary statistics have nice distances we can compute?
So in a way, yes, but in a way you could play with your summary statistics so that for fixed distance they play a similar role. See what I mean? Like, if you have a fixed summary statistics, then you have to play with the distance. But if you can choose the summary statistics, then the distance it plays a role, but in a way, you can rewrite the distance so that you can rewrite your summary statistics so that you use the correct distance. Do you see what I mean? I don't know how to formulate that in the correct way. But it does play a role. It does play a role. It's just that if it's smaller dimensional, it does not impact as much. Yes?
So if we have to check for a sufficient statistic, we would need the density, right? Generally, we look at the ratio of the densities at different points and see if it's only depending on the sufficient statistic, right? But we don't have a closed form distribution here. So even if we have a statistic, how would we check it's sufficient or not?
This is my answer. So, as you say, it's very, very tricky to identify summary statistics. So, they are particularly useful if data are exchangeable. What do I mean by data exchangeable? If your model doesn't really return only one simulated data, but a sample. Imagine a very basic simulator, which we don't want because you don't use ABC, that will just return a normal sample. Okay, imagine that for a second. And then your data are a normal sample simulated from this model. And you want to compare. You're not going to compare just the raw distance between each sample. You're going to use a summary statistic like the mean, the variance, or something. If your data are exchangeable, if they are sampled from a distribution or from a model, then you need summary statistics. That's the best example where you need it. You need it in many other cases. So how do we choose it? There are many algorithms that exist. It's still a work in progress in the sense that some people are still coming up with new ideas. on how to do it. Because as you say, we cannot prove in advance that something is going to be sufficient, except if you know exactly your model, if you have a very simple model. So there are different types of approaches. Most of them imagine that you have a set of possible summary statistics that you came up with, like you have the ideas of many summary statistics. Some approaches try to identify a subset of these summary statistics, because of course you could take all of them, but it will be computationally much more expensive because you are in a high-dimensional space and you will want to compute distance between all of them. Then no point of doing summary statistics. You could have used the data. So the idea is to find the smallest possible set that summarize enough information to do a perfect posterior inference. And so here I have two references on that. Then the other algorithm is to project the summary statistic on a lower dimensional space. I'm not going into the detail of that, but I just want you to know that a lot of people are working on it. I even forgot to cite my own paper on it. Should have done that. Huh? But yeah, there are ways, but it's approximate ways. So it's really algorithm and ideas of how to do it in practice. My big warning is that all of these methods will never replace a good choice of what do you really want to learn about. So do you really want to learn about this posterior? Or in fact, you just want to learn about this posterior with a specific eta that you like? If this is enough for you, then use the eta that you like. Like, you know, like if from expert knowledge you know that in fact you don't want to learn about the whole population, but you want to learn about the mean of the population, then use the mean. Like, talk with your, well, I say collaborators, except if you come across your own model, but usually you work, as a statistician or machine learner, you work with people with real problem. And think together about what will be summary statistic that makes sense for the problem. Yes?
I think it's very interesting that you cast in the light of making an error in the first place, because really when you look at these posteriors that are indexed by a function eta, you could choose, I don't know, some predicted loss or something to make sure that your model actually does what you want it to do downstream in the tasks. So I don't actually think of ABC primarily as an approximation to the exact posterior. I think of it as a different way of arriving at a posterior belief. I think in that vein, this is really, really cool stuff.
Yeah, so there is a lot of, well, there is not a lot, there are two very good papers on that. I decided not to talk about it because I had to choose what to talk about, but I can give you reference on this too. Okay, no, I will take more questions now because then we go into something slightly different. Yeah?
How do we know if the model is picking out nonsense? We're making a lot of approximations here. Like, how do we do any type of checking?
To know if the model makes sense or to know if we are doing wrong approximations?
Well, approximation. So I assume that the model is correct.
Okay.
It's a very strong assumption.
I agree. So assuming the model is correct, we know that if epsilon goes to 0, that's fine. And I have some theoretical result at the end of this session on how can we make sure that we are converging. Any other question? Yes?
Sometimes I hear about when we can have these really complicated models, at least in computational neuroscience, like when we're trying to get enough data to kind of constrain the parameters of these models. Like some people are saying these are very under-constrained because we don't really have enough data. Is this an example where ABC can be kind of useful in the sense of like, we don't really have a lot of data, it's good to kind of get certainty around parameters that are kind of constrained? Because I guess I don't really know exactly what means by under-constrained.
I don't know why ABC would work better than other Bayesian inference in that sense. Okay. You know, ABC compared to other, in the Bayesian setting, and yes, Bayesian setting will be good for that, but in the Bayesian setting, ABC is better only if you don't have the likelihood and you can only simulate from your model. If you can compute the likelihood, please use it. Huh? Please use Stan or other algorithm. Don't do ABC if you can do likelihood-based inference. But sometimes it's better to do ABC than making up a likelihood. Yes?
Yeah, what you just said presupposes that the likelihood actually makes a lot of sense, right? So if you can't write down the best likelihood than the one you currently have, but you still want your model to perform well, let's say predictably, you could well, I think, run into a situation where this actually works much better than exact Bayesian inference.
Exactly, yeah. And because sometimes you can write a likelihood where you're not sure it makes sense, you can use great algorithm to do MCMC or more improved MCMC, but then you have not much control of the error, because if you're not sure on your likelihood, then you don't. Here you can control the error. It's by putting epsilon to 0. It might not be feasible, but you can control it. If you made up a likelihood, then how do you evaluate how bad your results are? Well, it's how bad is your likelihood, and if you cannot evaluate that. Okay. So here I assume that we have this algorithm. Again, that's the ABC algorithm. But that we don't want to throw away any data anymore. So because we spent a lot of time simulating all these data sets, all these auxiliary variables Z. The algorithm is to throw them away if the distance is too small. Epsilon could be fixed in advance or quantile. Can we not use the one that we want to throw away to kind of help our posterior? So that's the idea of post-processing using weights. So there are kind of two ideas on post-processing. So imagine now you don't throw away any of your simulated data. There are two ideas. One is you re-weight your particle according to the distance. So if they had a large distance, you weight them with a small probability if they have a small weight. If they have a small distance, you put them with a highest weight. So that's the idea number one. The idea number two is that you use local regression to project or regress, or to change the value of your parameters, basically. So you use the ABC, and now you're going to do a regression to slightly change the value of this parameter so that you take into account the fact that the distance between the simulated data and the observed data is big. So I have one illustration here, but I will have one illustration in the next slide. So the idea is not that complicated. I find it not that intuitive, but not that complicated at the same time. So imagine you have all this theta I coming from your ABC. So the theta I are these here. And they come from your ABC. You don't want to throw anybody away. And you're going, so you know that this theta I basically, on average, if you had a lot of them, they will not converge to the real posterior. They will converge to a posterior that is related to the Zi associated, to the epsilon associated to the theta I. So you want to correct for that. So you want to correct for the fact that you were aiming for the mean of this posterior here for the Zi, but in fact what you wanted is the mean with the real observation. So you do some regression saying, my theta I comes from a posterior, but in fact its mean depends on the Zi that are far away potentially from the real observation. So I will recorrect for that. I show you, I hope it's in the next slide. Yeah, I show you an example or a figure. Again, it comes from this review article. So here, T is the summary statistics. Theta is your parameter, is one-dimensional. So theta is on the y-axis. T is on the x-axis. And the dots are things that you simulated. So here, for example, you simulated an observation. You simulated for a value of theta, around 0.3. And what you obtain from your simulator is a summary statistic of equals 0.9. Here, you sampled this value of theta, which is around 0.6, and when you run your simulator, you obtain a summary statistic around 0.8. You see what I mean? It's a bit of a strange way to see it. You sample theta from the prior, you run it through the simulator, you simulate your data, you use the summary statistics, that is called T here, and you plot on the x-axis the value of T, on the y-axis the value of the parameter at the beginning. So if we have all this cloud of points, but we have all this cloud of points. The ABC, now we need an observation, because we have just a cloud of points. We need an observation. The observation is a blue line. So imagine that what you observe is this blue line, is this value, 0.85. So the idea is just to project, so it's to fit a model, here a linear model, but it could be another type of model, to fit a model and then project all of these dots towards the line on the middle here, just to correct for the difference. It's a tricky one, and I'm summarizing 2 long papers on one slide. So I can imagine that it's not that easy to grasp. But that's the idea of the post-processing. There are different ways of doing this regression. Some people, originally the idea was to do local linear approximation adjustments. That's the idea from Beaumont and al. And now there has been more different nonlinear regression approach, either using neural network or using kernel ridge approximation regression. So that's different approach to do the regression. The basic idea is to do projection. One potential big problem of that is that basically your parameter, once they've been projected, they might not stay and live in the same space of the prior before. So imagine your prior was a uniform between 0 and 1, but you do this projection, you might end up outside of your prior, which is potentially problematic. So it's just to finish on the post-processing, because it's a tricky, I don't want to spend ages on it, and it's a tricky thing to explain in a few minutes. I can answer a question on that later or tomorrow. But it works very well, so I could not mention it. Here's an example, again, with our model averaging, mean average. So the black line is a true one. The blue is ABC posterior. The red is the one with correction. For theta 1, it doesn't, so on the left-hand side is when we use a 0.1 quantile. On the right-hand side is when we use a 20% quantile. So if you use a 0.1 quantile, it doesn't make a huge difference. And here they are on top of each other. So really, there is no real point of doing all this thing that is super complicated to code, or not that complicated, just for that. But on the 20% quantile, it makes a huge difference. And 20% quantile means that you've decreased a lot your computational cost. So just on having much less computational cost, you can improve considerably your posterior distribution. Is there any question here? Yes?
Can you go back to the projection slide, the one with the picture? So you only project the points that are beyond a certain distance, the epsilon distance?
So here you take all of them. So if you were doing rejection algorithm, you would use a distance here. And you know, if I had time to do myself this picture, that's what I would do first. So you would use a band around the summary statistics here. So you will do a band here, and you will only take those and contribute posterior. Here you use everybody, so you use all these dots, and you project all of them. So in a way, you're increasing your computational power, because you can use all the particles that you've simulated. You don't reject anything. You just project.
But you wouldn't reject the ones within the epsilon bound.
No, but all the ones that are outside, you would reject them. Here you don't have to. Yes?
So it seems like this algorithm's convergence, or like how well it does, is based on a couple parameters you really have to define, like the epsilon and stuff like that. Is it difficult to compare across papers, like if someone chooses a different epsilon, or like how easy is it to tell like whether or not someone did something in the correct way, or it's like easy to reproduce someone else's work in comparison to like, because it seems like there's a lot more with an explicit likelihoods and such. There's a very clear like way to do the inference, and it's not so hard to compare across the works.
In a way, if you say exactly what you're doing, if you say which epsilon you're doing and which distance you're doing, it's completely reproducible. Well, as long as you have the data, of course, but that's the same problem with any MBC, any Bayesian. So there is no reproducibility. The algorithm is pretty simple. It's simpler than any MCMC where you have some proposal, etc. Yes?
When you did a re-rating on the previous slide, how is that actually then different from report time?
So I didn't explain the re-rating. So I didn't explain the re-rating because we can talk about it individually. I didn't want to lose everybody with all the post-processing. Again, the post-processing is tricky because either I want really to explain it fully, and then it takes an hour. So I hesitated not to mention it at all, but at the same time, it's so powerful in terms of in practice that I cannot just ignore it and not mention it. But I didn't give enough detail for you to grasp all the ideas, so I can answer them just offline. Okay? So I have a few more slides. I think I have 5 more slides before the end, so we'll finish earlier so that everybody can rest, but I'm conscious that you had a longer day. So I'm here. Okay, I was wondering where I am. So I just wanted to finish with some theoretical results. I'm not going to prove anything, don't worry. I just wanted to state some theoretical results. And to be completely fair, I don't derive any theoretical result like that, so you cannot ask super complicated questions. Because I'm learning myself, well, I learned myself them a few years ago, but it's not as if I can prove them. Some people are great at proving these things. So what is the type of theoretical result that Bayesian do usually is, as we talked about like from the online person, if we accumulate more and more data, we assume that the posterior will converge or stabilize around a true value. If we assume that there is a true value, assume our model is correct. So here, now the x star, the data, will be a function of n, just to say n is the number of data we have. So if n increases, so if we have more and more and more data, and the true model, so the data have been generated with some true parameter theta 0, then we expect our posterior to converge towards this value of theta 0. So the way Bayesian consistency and all people who do proof about Bayesian write it is that they say under the posterior distribution, our posterior will put less and less mass outside the ball around this theta 0. So imagine you have this theta 0, the real one, and this complicated things here just tells you that outside of this theta 0, so for a ball around theta 0 with diameter delta, it will give less and less weight outside. So more data we have, more we are going to concentrate very close to theta 0. That's what Bayesian care about when they do a theoretical result. In ABC, we have an additional thing, is that, so we have an epsilon in addition. So we want n to goes to infinity, but we also want to go epsilon to goes to 0. So people who do proof, they have to make very clear and careful choice about how they prove that, and they have to make sure that epsilon converges to 0 and n goes to 0, infinity. Of course, everything depends on the choice of the summary statistics. We already said that. It's not going to change. So what people can prove is that, as we expect, when the number of data increase and epsilon goes to 0, then we have the same result as before. If there is a true parameter theta 0, everything will concentrate into this true parameter. So that Bayesian consistency. Yes?
Okay, but if epsilon doesn't go to 0, like in practice, we are not going to run millions of experiments.
Next slide. Is it next slide? Yeah, here, this is just technical detail, is that one of the assumptions of the algorithm, of the proof, is that there is a concentration of eta, and I just wanted to make sure that I don't give you a wrong slide. I just wanted to make the definition of what means concentration of eta. It's some condition of the summary statistics, just making sure that the summary statistics summarize well enough the data. So if the number of data increase, the summary statistics converge to a place that is a deterministic function of theta. That's just proving that everything works. Now, the second result that is really related to what you just said is the posterior, the posterior consistency that I talked about only guarantees that when the number of data increase and the threshold stands to 0, it will stabilize around a particular value theta 0. So everything will concentrate there. But we don't know at all how the shape of the concentration is. Is it going to be a uniform, a normal? So for those of you who does, well, I'm going to ask you a question for once. What is the most common distribution that For example, the central limit theorem. What is the distribution that it concentrates to? Well, I had heard too many things. Yes, normal. So frequentists and Bayesian also, but mainly Bayesian people who does a theoretical analysis love normal distribution. Because when you have a normal distribution, if it converges to a normal, you can prove many things. You can prove that the coverage is Bayesian. You can prove so many things. They are so happy. I cannot tell you. So we would love to have a normal distribution as a convergence. What they prove in this paper, and that's a very recent paper, is that, so they have to take into account sigma n, which is the rate of convergence of the summary statistics towards the real value. If sigma n's over epsilon n being the threshold, so it goes to 0, 2, if the ratio tends to 0, then the posterior convergence, the posterior will converge to a uniform, which is something, it's some results, but it's not great from a Bayesian theoretical perspective because we prefer normal distribution. If we want a normal distribution, we need to have sigma n much bigger than epsilon n. So they proved in this paper that if sigma n is much bigger than epsilon n, it's possible to prove that the posterior will converge towards the real area, but in addition, it will converge in a normal distribution way. So what the theoreticians recommend, so if you use this algorithm, the theoreticians say, in fact, we don't want epsilon to be as small as possible. It's not such a problem if epsilon is not 0. What we really care about is that sigma n is much bigger than epsilon n. So if you cannot put epsilon to 0, because in practice you cannot, make sure that sigma n. Then there is a question of how to control sigma n. This is on the paper. That's a question I'm not going to answer, I tell you right now. Yes?
So for the conversion of eta to some fixed function of b of beta, I'm wondering whether this sigma n is actually well defined if this doesn't happen uniformly over beta. You need, it's the beta 0, so it converges to the true value.
Yeah, it converges to the true value. So there is two things. It converges to a true value if it's the data, and if it's the simulated data, it converges to a value that's a function. Yeah? You answered your own question. That's perfect. Yes?
Is the condition about beta converging slower than posterior about exploring the space of the statistic?
I think it could be explained in a way like that. I talked to one of the co-authors, and it's difficult to put it into words. You know, when you start doing proofs, you do the proof. And you're not thinking about trade-off. We are not yet there in the field. That's fine? Any other question? So I believe it's my last slide of the day, or maybe my one before last. I said I will not talk about it, but I wanted to mention it in one slide because I cannot not talk about it. It's model misspecification. You've all heard this quote. Huh? I'm not going to be the first one, but it's so true when you are working on real problems. Models are always wrong. Always. And so all what I've said so far assumed that the model was true. And all what I'm going to say tomorrow assumed that the model is true. And all what you hear ever in Bayesian, or most of the time, is assuming the model is true. You need to do something when you have a problem, and assuming the model is true is sometimes the best thing you can do. You have to keep in mind most of the time that your model might be completely wrong. If the model is wrong, some people are working on it. I didn't want to do a literature review on how to do Bayesian under model misspecification. So if you're interested, there are very, very good work out there. If the model is wrong, some people have done some theory. ABC is still working pretty well. So ABC will still converge towards a distribution that makes sense in the sense that is the closest possible projection towards the set of model you consider. So again, I can explain those of you who want later. But in fact, ABC does behave pretty well even if the model is wrong. Well, the best it can, in a way. But the posterior obtained when you do this projection that I talked about does not work that well. So if you believe your model is wrong, don't do the projection, because some theoretical results show that it might give very bad results. It's improving a lot when the model is correct, but it might give very bad results if the model is wrong. So that's, I think, the message I want you to have on model specification. This is just a summary of what we discussed today, and tomorrow I will come back to the same slide, just for you to come back with a fresh mind. Why do you want to use ABC? What is ABC? And what did we cover today? I think you deserve to have a good dinner and a night of sleep. And I'll see you tomorrow morning.